All right, guys, so let's take a look at these. This homework assignment on page 333. So does everyone have it out? Okay. So tell me which questions you had difficulty with. Does anyone need me to do number 9? No. 13? 15? 17? No. 21? 21? 24? 31? 37? 39? No, and 43? 43, okay. So let's go ahead and take care of these 3, and then I'll lecture on today's material. And if you're ready to give them to me, I'll go ahead and collect them from you, and we'll put them in the folder and start the next batch of material. All right, so 21. 21 in the book says that you have some ionic substances. You have KF, you have CaO, and you have SCN. And it says that they are isoelectronic. So what does isoelectronic mean? Same number of electrons, okay? It says examine the lattice energies for these substances in table 8.2 and account for the trends that you observe. All right, so let's go to table 8.2. And let's write down what these lattice energies are. And then we'll define them, and then we'll talk about why they are what they are. All right, so table 8.2, does anyone know where that is? What page it's on? Okay, it's on page 301. Okay, so if we look up KF, it's 808. If we look up CaO, it's 3414. And if we look up SCN, it's 7547. Okay, so let's come up with a definition for lattice energy. I mentioned it very, very briefly in class, right? All right. These numbers are in kilojoules per mole. And before we go any further, let's talk about what kinds of substances are these? What do we expect for these to be? So KF, potassium fluoride, what is this? If I go in the lab and I look for this potassium fluoride, what do I look for? Madison, you were going to say something? It's an ionic compound, right? You can tell because you've got a metal and a non-metal. What do ionic compounds, what's the generic term for them? It's a salt. So I basically go in the lab and I look for these 3 salts. And they might be slightly different. They might be slightly different color. They might be slightly different shape of crystals, but they all look like salts. Okay? So what lattice energy is the energy that you need to take that salt and separate the ions and turn those ions into gaseous ions. Okay? So in a sense, it's the energy that you need to melt that crystal and then vaporize it. Okay? All right. So take a look. Who is going to require the most energy to separate those ions? No, look at the numbers. Okay. So this takes the most energy. To separate the crystal, right? And vaporize the ions. So the question is, why? Right? Isn't that kind of what they were asking? Why? If it takes the most energy to separate those ions, what does that tell you about the ionic bond? It's really strong. It's a really strong ionic bond. All right? So what does that now leave you with? It leaves you with 2 other substances that take less energy. So what does that tell you about the strength of those ionic bonds? Which one is the weakest? KF is the weakest of these ionic bonds. And then CaO is kind of in the middle. All right? What makes the difference in the strength of the interaction? What's going to give you a stronger ionic bond? Charges and radius. All right, so the bigger the charge of the ions that are coming together, right, or the bigger the charge difference, you would expect would give you a stronger ionic bond, right? We talked about that a little bit in class. All right, so let's take a look at the charges of these things. So what's the charge of potassium and fluorine? +1 and -1. What about calcium and oxygen? 2+ and 2-. All right, and if we think about where these things are, potassium and calcium in the same period on the periodic table? Are they in the same row, basically? So they have about the same radius because they're right next to each other, right? How about fluorine and oxygen? Are they pretty much like next to each other? All right. So why is calcium oxide stronger than the potassium fluoride? It's not radius. It's charges. Okay, you've got twice as much charge attracting in calcium and oxygen than you do in potassium and fluorine. All right? So that pattern is easy enough to predict. What about the scandium and the nitrogen now? All right, well, what's the charge of nitrogen? What is it? Well, it's 3- in this case. Where is scandium on the periodic table? It's 3d1. Sc, right? 3d1. What's the charge of that typically? Well, it's 4s2, 3d1. So how many electrons do you think you could lose? One or three? Wouldn't it be 2 or 3? Oh, smart girl. Yeah, it's 3+. Because if you call nitrogen 3-, you have to call scandium 3+ to balance out. Okay? All right, so why is that a stronger bond? Huh? Because the charge is bigger. It has nothing to do with radius, because if you look, where's scandium on the periodic table? It's next to potassium and calcium, so the radius of scandium is going to be about the same, right? And if you look at where nitrogen is in comparison to oxygen and fluorine, again, they're right next to each other on the periodic table, so the radii there is about the same. So in this particular question, radius is, since it's pretty much constant, is not a factor. It's the charge. The bigger the charge difference, right, the stronger the ionic bond. Fair enough? Okay. All right, let's take a look at question 24. 24 is a similar question. And in all actuality, if they ever ask anything about lattice energy on the AP exam, it's going to be like this one. Okay? All right, so for question number 24, they're telling you that you have CaF2, and they're telling you that the lattice energy of CaF2 is bigger than BaF2. And you have to basically explain why that is. All right, so let's take a look at placement on the periodic table. All right, so what is the difference between these two compounds, first of all? What's the difference? One has calcium, one has barium, right? Where are these two elements on the periodic table with respect to one another? Are they in the same family? Yeah, they are. Look, calcium's number 20, it has a charge of 2+. Barium is number 56, it has a charge of 2+ as well. All right, fluorine is 1- in both cases. The charge difference is the same in both cases, right? So you can't make an argument that this guy has a bigger lattice energy because it's got a much higher charge and the ionic bond is stronger. You can't make that argument, okay? All right, so what is the argument here? Okay, think about the structure of calcium versus barium. How many shells does calcium have? 3. How many does barium have? How many? 5? 6? Okay? All right, so why would being bigger make that ionic bond weaker? Shielding. Did you say that out loud, Dallas? Good for you. Shielding. Okay, this is shielded. This nucleus is shielded. It cannot make as strong an ionic bond, so then it's not going to take as much energy to melt that crystal and vaporize those ions. Okay? Make sense? Yes? It does. I just didn't draw it because I ran out of room. Calcium has 4, and barium should have 6. Okay. I just got lazy. Look, calcium's number 20. It's in the 4th row. Barium's in the 6th row. Okay. All right. Let's take a look at the next one. What? Yeah, I miscounted. Okay. All right. How about sodium chloride versus rubidium bromide? All right. I think it's safe to say the first thing you should do is write the charges on these things and see if the charge is what is causing that lattice energy difference. So what's the charge on sodium and chlorine? +1, -1. What about rubidium and bromine? +1, -1. All right, so charge is not the key player here, right? Charge differences are not the key player. So if charge is not the key player here, then what is? Radius. Okay. So you don't even have to look at the periodic table to tell who's going to have the bigger radius, right? Which one has the bigger radius? The bigger radius ultimately ends up with the weaker ionic bond, right? Which of the two has the weaker ionic bond? Okay, this one. And why does radius matter? Because the bigger you are, the more shells you have, the more shielding you have. All right? So this one's weaker because the radius is larger. And there's more shielding. Okay? This one has fewer shells. That nucleus isn't shielded as well. They can stick to one another very well. Okay? All right, let's take a look at, oh, they had given me a third one in that series, huh? They had given me cesium bromide, too, at the end of this. Oh, I'm out of room. So cesium bromide. Same thing here, right? This is +1, this is -1. There is no charge difference. It's got a lower lattice energy, so what does that tell you about the radius of the cesium? It's got to be even larger than the rubidium. Is it? Look at the placement on the periodic table. Does cesium come below rubidium? Sure does. Okay? All right, let's take a look at the last one, BaO versus KF. Okay, start by writing the charges on these things first. All right, so BaO, barium is 2+, oxygen is 2-. KF, +1, -1. Do I need to go any further? Why does it take more energy to melt that barium oxide than it does potassium fluoride? You've got a bigger charge difference. Okay? Make sense now? All right, great. Let's take a look at 43 and we'll be done. It says, in the following pairs of binary compounds, determine which one is a molecular substance and which one is an ionic substance, and use the appropriate naming convention to assign a name to each compound. All right, we can do this. Let me just rip this page out and flip to the back. All right, so let me just write them all down because I want to flip to a table in the book and I want to show it on the screen. So we've got SiF4 and then we've got LaF3. B is FeCl2 and ReCl6, and then C, PbCl4 and RbCl. All right, so to answer this question, you really need to look at electronegativities, and there's a table in your book. It is on page, I want to say 308. Looks like this. Okay. You need this to be able to answer this question. Okay. All right, so what you do in this case, starting with SiF4, is you look up the electronegativity value for silicon, and it happens to be 1.8. And then you look up the electronegativity value for fluorine, and you subtract them. And you do the absolute value of that. All right, so 1.8 minus 4.0 is 2.2. And that tells you what kind of bond this forms, right? So if the electronegativity difference is greater than 1.5, what do we call these? Ionic. If it's less than 1.5, then what do we call it? Covalent. So if your electronegativity difference is greater than 1.5, you use the ionic naming rules. If it's less than 1.5, you use the covalent naming rules where you use the prefixes. Okay? So here we don't have the luxury of using prefixes. That would be too easy. So instead we're going to use the ionic naming rules. What would we call this? This would be called silicone. No prefixes, remember? What is it in the book? Tetrafluoride. That's what they have in the back of the book? Yeah. Okay, they call it silicone tetrafluoride. We'll have to see why that is. Okay, next one, LAF3. So same thing again. You look up lanthanum. Lanthanum is 1.0. Fluorine is 4.0. That's a 3.0 difference. That's an ionic bond, right? They have chlorine. Let me see. 43. No, the first one is fluoride. Is there a mistake in the back of the book? 43A. Yeah, SiCl4, okay. The question in the book says SiF4. They answered it for Cl4. If you were to take the difference of chlorine versus fluorine, the difference would be 1.2. And then you would have to name it using the molecular naming conventions. But because in the actual question in the book it said fluorine, the difference is 2.2, you use the ionic naming convention. So what I would call this is silicone, and just to be on the safe side, I would put a Roman numeral in there to denote the charge of silicone, particularly because you know silicone's in a bad spot on the periodic table, right? So I would call it silicone fluoride. All right. LAF3, same thing, because that electronegativity difference is so great. It's going to be an ionic bond. Use the ionic naming rules. And when you have these weird things that are in bad places like lanthanum, where it's a transition metal, it's always safest to err on the side of putting the Roman numeral in the middle. Okay? So I would call this lanthanum. What's the Roman numeral here? 3 fluoride. Okay? All right, let's take a look at the next one, FeCl2. Same thing. Use the chart, come up with the electronegativity difference. So iron is 1.8, chlorine is 3.0. So 1.8 minus 3.0 is? What is it? 1.2? This is kind of cutting it close though, right? Because according to that number, you should go ahead and use the molecular naming rules, but we know this isn't molecular, it's ionic, right? Because it's a true metal and non-metal. The times that you want to do this business of subtracting electronegativity differences is really when that first element is a metalloid, okay? When you have these ambiguous situations. But in this case, I wouldn't even bother. I know it's ionic. This is iron 2 chloride. All right, let's take a look at ReCl6. Where's Re? It's at the bottom. It's 1.9 minus 3.0. This is 1.1. Okay. But in this, and again, in this case, based on that in itself, you would use the naming rules for a molecular substance. What's the answer in the back of the book for this one? What they say for this? For 43B, the ReCl6, what they call it? They called it molecular? What is Re? What? Rhenium? I don't know. My periodic table doesn't have names on it. R-E-N-I-U. And if we're going to use the molecular naming rules, what would you call this? Hexachloride. Okay. All right, PbCl4. Pb, where are you, Pb? It's 1.9. Cl is 3.0. Oh, here we're in another weird situation again. Because this difference is how much? How much is that difference? Hang on, that wasn't a 1.1. Wasn't that a 2.1? It is 1.1. So this is 1.1 again. But we know for a fact this isn't molecular because lead is a metal, right? So what would you call this? This is lead 4 chloride. All right. And then the next one, RbCl, Rb rubidium is 0.8. Chlorine is 3.0. This is 2.2. And this is rubidium chloride. Okay. So really, this business of using the electronegativities to figure out naming, use them only when you have an ambiguous situation when that first element is a metalloid. Okay. Outside of that, if you know flat out that that first element's a metal, you just go ahead with the ionic naming rules. Okay? Huh? Well, that's kind of a weird thing, isn't it? Okay? By flat out metals, I'm talking alkali, alkaline earth, and maybe those first two rows of the D block. Okay? Once you start seeing F orbitals in places, we stop seeing patterns. Okay, all right. Okay, so let me stop this.